Welcome to the Deep Sleep Discoveries channel. Settle in as we explore the invisible force that holds everything together. Gravity is the gentle hand that keeps your feet on the ground, the architect of galaxies, the sculptor of stars. Just before we begin, if you enjoy these calm, curious science explorations, please consider liking this video and subscribing to the channel. It helps others find their way here too. Tonight, we'll journey through 100 facts about this cosmic embrace, each one a small window into the force that connects us all to the universe itself. Let these truths about gravity carry you softward into rest. Gravity is the weakest of the four fundamental forces in nature, far less powerful than the electromagnetic force, the strong nuclear force, or the weak nuclear force. A small refrigerator magnet can overcome the gravitational pull of the entire Earth when it lifts a paperclip. Yet despite its weakness, gravity shapes the cosmos because it acts across infinite distances and always pulls in the same direction, never cancelling itself out. This paradox of weakness and cosmic dominance makes gravity perhaps the most quietly powerful force we know. Its gentle persistence built everything you see. Gravity always attracts in everyday experience, though dark energy creates a repulsive effect on cosmic scales. Every gravitational interaction you've ever witnessed has been one of pulling, of drawing together, of embracing. Unlike magnetism with its north and south poles that can push away, gravity only knows how to gather. On the vast stage of the universe, dark energy acts like an anti-gravity force, pushing galaxies apart. But here in our corner of existence, gravity remains the universe's way of saying everything belongs together. It is the force of cosmic companionship. Every object with mass exerts gravitational pull on every other object, no matter how small or distant. Right now, you are pulling on the moon with your gravity, and the moon is pulling back on you. You attract every star, every planet, every grain of sand on distant shores. The book on your shelf pulls on mountains across the ocean. This universal connection means nothing in the cosmos is truly isolated. We are all gravitationally bound to everything else, participating in an eternal dance of mutual attraction that spans the observable universe. The strength of gravity depends on mass and distance, following a precise mathematical relationship. Double the mass of an object and you double its gravitational pull. But double the distance between two objects and the gravitational force becomes 4 times weaker. This inverse square law means gravity weakens rapidly as you move away, which is why we feel Earth's pull so strongly but barely notice the sun's despite its enormous mass. The equation is simple, yet it governs the motion of everything from falling leaves to orbiting galaxies, an elegant rule written into the fabric of existence. Gravitational waves travel at the speed of light through the fabric of space-time. If the sun suddenly vanished, Earth would continue orbiting an empty point in space for 8 minutes and 20 seconds before the change in gravity reached us. Gravity isn't instantaneous. It propagates as ripples through the universe at the cosmic speed limit. These waves carry information about massive collisions and catastrophic events across billions of light years. When we detect them, we're feeling the universe itself vibrate, experiencing echoes of cosmic violence that occurred when Earth was young. Gravity moves, flows, and travels like light through darkness. Isaac Newton formulated the law of universal gravitation in 1687, giving humanity its first mathematical description of how objects attract each other. His equation was breathtakingly simple. The force equals the gravitational constant times the product of two masses divided by the square of the distance between them. With this formula, Newton could predict the motion of planets, the trajectory of cannonballs, and the fall of autumn leaves with the same mathematics. For over 2 centuries, his law seemed to explain every gravitational phenomenon in the heavens and on Earth. It was humanity's first glimpse of a universe governed by comprehensible, universal laws. Newton's apple story may be partially true. He did contemplate falling objects and their connection to celestial motion. While the dramatic tale of an apple striking his head is likely embellished, Newton himself recounted that watching apples fall in his garden led him to wonder if the same force pulling fruit downward also kept the moon in orbit. This moment of insight connected the mundane and the cosmic, revealing that the same gravity-making objects fall also choreographs the dance of planets. It was a unifying vision that erased the ancient boundary between earthly and heavenly physics. Sometimes the grandest revelations arrive quietly. Gravity creates the sensation of weight by pulling your mass toward Earth's center. Weight is simply the measurement of how hard gravity pulls on you, which is why you'd weigh less on the Moon and more on Jupiter, despite your body remaining unchanged. Your mass, the amount of matter you're made of, stays constant throughout the universe, but your weight varies depending on which world you stand upon. When you step on a scale, you're measuring the conversation between your body and the planet beneath you. Gravity is what makes you substantial, what gives you presence in space. Mass and weight are different. Mass is constant. Weight changes with gravity depending on where you are in the universe. An astronaut with 70 kilograms of mass has that same 70 kilograms on Earth, on the Moon, or floating in deep space. But on Earth, that mass weighs about 686 newtons. On the Moon, only 114 newtons, and in orbit essentially nothing. Mass is an intrinsic property, how much stuff you're made of. Weight is relational, a dialogue between your mass and whatever gravitational field you happen to be experiencing. Your essence doesn't change, only how the universe pulls on it. The gravitational constant, represented by g, is approximately 6.674 times 10 to the negative 11th power in standard units. This number is one of the fundamental constants of nature, appearing in every gravitational calculation throughout the universe. It's remarkably small, which reflects gravity's weakness compared to other forces. Measuring g with precision is surprisingly difficult. It's one of the least accurately known fundamental constants because gravity is so weak that tiny experimental errors have large effects. Yet this small number governs the architecture of galaxies and the formation of stars. The universe speaks in subtle mathematics. Gravity works the same way throughout the entire universe, following identical laws on distant galaxies as it does in your living room. The same equations Newton and Einstein developed here on Earth describe the motion of stars in galaxies billions of light years away. This universality is one of the most profound discoveries in science. The laws of physics don't change with location or time. Gravity behaves identically in the distant past as it does today, in remote galaxy clusters as it does in your neighborhood. We live in a cosmos of consistent rules, a universe where the same forces guide both atoms and galaxies. There is no such thing as zero gravity, only microgravity, where gravitational forces are present but their effects are imperceptible. Astronauts on the International Space Station are still within Earth's gravitational field, experiencing about 90% of the gravity present at Earth's surface. They feel weightless because they're in continuous freefall, falling around Earth at exactly the speed needed to keep missing it. The station and everything inside it falls together at the same rate, creating the illusion of floating. True zero gravity would require being infinitely far from all mass, an impossible destination in our universe filled with matter. Gravity affects time itself, making time pass more slowly in stronger gravitational fields in a phenomenon called gravitational time dilation. A clock on Earth's surface ticks slightly slower than an identical clock on a satellite. The stronger gravity at Earth's surface literally slows the passage of time compared to weaker gravity in orbit. This isn't an illusion or measurement error. Time genuinely flows at different rates depending on gravitational strength. The universe's clock runs at different speeds in different places. Time and gravity are intimately connected, two aspects of a deeper reality that Einstein helped us understand. Gravity bends space as well as time, warping the very geometry of the universe. Massive objects create curves in the fabric of spacetime like a bowling ball, creating a depression on a stretched rubber sheet. Objects moving through this curved space follow paths that seem bent to outside observers. Light itself follows these curves, taking the straightest path through curved space. The geometry of the universe is not fixed but dynamic, constantly reshaped by the presence of mass and energy. Space is flexible, responsive, alive with gravitational influence that transforms its very structure. Albert Einstein revolutionized our understanding of gravity in 1915 with his general theory of relativity. He showed that gravity isn't a force pulling objects together, but rather a curvature of space-time caused by mass and energy. In Einstein's vision, objects don't fall because they're pulled. They follow the natural curves in space-time created by nearby masses. A planet orbits a star not because of some invisible tether, but because the star's mass curves space-time into a shape where orbital motion is the straightest possible path. Einstein transformed gravity from a force into geometry, revealing a universe far stranger and more beautiful than anyone imagined. Einstein's general relativity describes gravity as curved space-time, where mass and energy warp the four-dimensional fabric of the universe. Imagine space-time as a vast, flexible sheet that can be stretched, compressed, and curved by the presence of matter. The Sun creates a deep well in this fabric, and Earth rolls around the edge of that well, perpetually falling but never reaching the bottom. Every massive object creates its own curvature, its own gravitational signature in the geometry of existence. This vision united space and time into a single entity, showing that they cannot be separated. The universe is a tapestry of warped geometry. Mass tells space-time how to curve. Space-time tells mass how to move, a poetic summary of Einstein's field equations. Objects with mass create curves in space-time, and those curves determine how objects move through space and time. It's a conversation, a feedback loop between matter and geometry. The Sun curves space-time, which guides Earth's orbit, which in turn creates its own smaller curvature affecting the Moon. Everything is both sculptor and sculpture, both artist and canvas. This reciprocal relationship creates the intricate gravitational choreography we observe throughout the cosmos, from binary stars to galactic superclusters. General relativity predicted black holes decades before we found them, describing regions where space-time curves so extremely that nothing can escape. Einstein's equations allowed for solutions where gravity becomes so intense that it creates a one-way boundary in space-time. Even Einstein himself doubted such extreme objects could exist in reality. Yet the mathematics insisted, if enough mass concentrates in a small enough space, space-time must curve into these cosmic prisons from which even light cannot emerge. The equations knew about black holes before we did, waiting patiently for reality to confirm what mathematics had already revealed. Theory preceded observation by half a century. Einstein's theory predicted gravitational waves in 1916, describing ripples in space-time itself that propagate outward from accelerating masses. When massive objects move violently, like two black holes spiraling together, they create waves in the fabric of space-time that spread outward at light speed. These waves carry energy, causing space-time itself to oscillate, alternately compressing and stretching as they pass. Einstein's mathematics showed that space-time wasn't just curved but dynamic, capable of vibrating like a drumhead. The universe could ring like a bell, singing songs of cosmic collision that travel across billions of light years to reach us. Gravitational waves weren't detected until 2015, confirming Einstein's prediction 99 years after he made it. On September 14th, two detectors in Louisiana and Washington simultaneously felt space-time stretch and compress by less than the width of a proton. The signal came from two black holes that had collided 1.3 billion years ago, sending ripples through the universe that finally washed over Earth. In that moment, humanity gained a new sense, the ability to feel the universe vibrate. We'd been deaf to gravitational waves since the beginning of our species, and suddenly we could hear the cosmos singing. Einstein was right again. The famous eclipse expedition of 1919 proved Einstein's theory by showing starlight bending around the Sun. During a total solar eclipse, Arthur Eddington photographed stars near the Sun's edge and compared their positions to where they appeared at night. The stars had shifted exactly as Einstein predicted. Their light had followed curved paths through the Sun's warped space-time. This was the first experimental confirmation that gravity wasn't just an attractive force, but a bending of space itself. News of the confirmation made Einstein an international celebrity overnight. The universe had spoken, and its message confirmed the strange geometry of general relativity. GPS satellites must account for relativistic effects of gravity, or they'd be inaccurate by miles within hours. Each satellite experiences weaker gravity than we do on Earth's surface, causing its onboard clocks to tick faster by about 45 microseconds per day. Simultaneously, the satellites move at high speeds, which makes their clocks tick slower by about 7 microseconds per day. The net effect is about 38 microseconds daily, which would cause position errors of several miles if uncorrected. Every time you use GPS, Einstein's theory of relativity is quietly working in the background. Your phone knows about curved spacetime. Gravity affects the frequency of light, causing gravitational redshift, where light climbing out of a gravitational well loses energy. Photons escaping from near a massive object must work against gravity, losing energy and shifting toward longer, redder wavelengths. Light falling into a gravitational well gains energy and blue shifts. This effect has been measured in laboratories with clocks separated by just a few meters of height. The light from white dwarf stars shows dramatic redshift because it must climb out of intense gravitational fields. Even the light traveling from your basement to your attic experiences this shift, though immeasurably small. Gravity changes everything, even light itself. Time passes more slowly on Earth's surface than on a mountaintop due to stronger gravitational fields at lower elevations. Your head ages faster than your feet, though by only a few nanoseconds over a lifetime. Atomic clocks on different floors of a building tick at measurably different rates. This isn't science fiction or theoretical speculation, it's measured reality. The ground floor of a skyscraper exists slightly in the past compared to the penthouse. Gravity reaches through time itself, slowing the seconds in its stronger embrace. Every vertical inch you climb accelerates your personal clock infinitesimally, adding up to a universe where elevation means aging faster. Astronauts in orbit age slightly slower than people on Earth, about 0.01 seconds slower every 6 months due to their high velocity. Two competing effects are at play. Weaker gravity in orbit speeds up their clocks, but their enormous velocity of 17,500 miles per hour slows their clocks even more. The velocity effect wins, making astronauts' time pass more slowly than ours. When they return to Earth, they've experienced slightly less time than people who stayed home. They've traveled into our future, if only by fractions of a second. Every orbital journey is a small step through time, a gentle passage forward that accumulates with each orbit. Earth's gravity accelerates objects at 9.8 meters per second squared, pulling everything downward with consistent force. Drop a stone and after 1 second it's falling at 9.8 meters per second. After 2 seconds, 19.6 meters per second. Each second adds another 9.8 meters per second to its velocity, creating the familiar arc of falling objects. This acceleration is so consistent that it defines our experience of weight and falling. Scientists have measured this value with extraordinary precision using laser interferometry and atomic fountains. It's designated by the letter G, a single letter representing the constant conversation between you and the planet holding you. Earth's gravity varies slightly depending on location, changing with latitude, elevation, and local geology. Gravity is about 0.5% stronger at the poles than at the equator. Mountains and dense rock formations create local gravitational anomalies. Satellites measure these variations to create gravitational maps of Earth, revealing invisible structures beneath the surface. Over the Indian Ocean, there's a region where gravity is noticeably weaker, creating a gravitational low point. These variations seem small, but they matter for satellite navigation, mineral exploration, and understanding Earth's internal structure. Our planet's gravitational field is subtly textured, varying across its surface like elevation on a topographic map. Gravity is slightly stronger at the poles than at the equator, about 0.5% more forceful, for two reasons. First, Earth bulges at the equator from its rotation, making the poles closer to Earth's center where gravity is strongest. Second, the centrifugal effect of Earth's spin partially counteracts gravity at the equator but not at the poles. An object weighing exactly 200 pounds at the North Pole would weigh about 199 pounds at the equator. This difference shaped human evolution, affected historical trade weight measurements, and influences modern satellite orbits. The planet beneath you is not quite a sphere, and its gravity reveals this hidden geometry. The equatorial bulge of Earth is caused by its rotation working against gravity, creating a planet wider than it is tall. Earth spins once every 24 hours, and this rotation creates centrifugal forces that push matter outward most strongly at the equator. Gravity tries to pull Earth into a perfect sphere, while rotation tries to fling it outward. The result is a compromise, an oblate spheroid, flattened at the poles and bulging at the middle. The equatorial diameter is about 43 kilometers greater than the pole-to-pole diameter. Our planet is shaped by the eternal tension between its rotation and its self-gravity, frozen into a geometry of balanced forces. You weigh slightly less on a mountaintop than at sea level because you're farther from Earth's center of mass. Climb Mount Everest and you'll weigh about 0.5% less than you did at the beach. Each kilometer of elevation reduces gravity by about 0.03%. The change is small but real and measurable with sensitive instruments. High-altitude cities like Denver have fractionally weaker gravity than coastal cities like San Francisco. This effect accumulates. If you could build a tower tall enough, gravity would continue decreasing with height. Every step you climb upward is a small escape from Earth's gravitational embrace, a tiny journey toward weightlessness. Earth's gravity extends infinitely into space, just getting weaker with distance according to the inverse square law. The Moon, nearly 400,000 kilometers away, still feels Earth's pull strongly enough to remain in orbit. The Sun's gravity reaches much farther, but Earth's gravitational influence extends beyond even Neptune's orbit, gradually fading but never reaching absolute zero. Every particle in the universe pulls on every other particle, so Earth's gravity technically reaches across the entire cosmos. The influence becomes unmeasurably small at great distances, but mathematically it never disappears. We are gravitationally connected to everything, everywhere, forever. The Moon is slowly drifting away from Earth at about 3.8 centimeters per year due to tidal effects and conservation of angular momentum. Earth's rotation creates tidal bulges in the oceans, and friction from these moving waters gradually slows Earth's spin. This lost rotational energy gets transferred to the Moon, pushing it into a slightly higher orbit. 4 billion years ago, the Moon was much closer, perhaps only 25,000 kilometers away compared to today's 384,400 kilometers. Each year, it recedes slightly farther, a gradual farewell playing out over geological time. Eventually, Earth and Moon will become tidally locked, eternally showing each other the same face. Earth's gravity keeps our atmosphere from floating away into space, holding the blanket of air that makes life possible. Gas molecules move randomly in all directions, but Earth's gravity pulls them downward faster than most can escape. Only the fastest moving molecules at the top of the atmosphere occasionally reach escape velocity and drift away. Mars, with weaker gravity, couldn't hold its atmosphere against the solar wind. Venus, with similar gravity to Earth, has kept its thick atmosphere for billions of years. Without gravity's constant embrace, our atmosphere would dissipate into the void within geological moments. Every breath you take is gravity's gift. Without gravity, Earth would be a scattered cloud of particles drifting through space, never cohering into anything solid. Gravity pulled together the dust and gas of the early solar system, accumulating matter into larger and larger bodies. As the proto-Earth grew, its gravity strengthened, pulling in more material in a runaway process. The compression from gravity heated Earth's interior, allowing heavier elements to sink toward the core while lighter materials rose. Gravity organized chaos into structure, randomness into order, dust into world. The ground beneath you exists only because gravity insisted that matter gather together. Every planet is a monument to gravity's patient accumulation. Ocean tides are caused by the gravitational pull of the Moon and Sun, stretching Earth's waters into an ellipsoid shape. The Moon's gravity pulls water on the near side of Earth toward it, creating a bulge. Simultaneously, on Earth's far side, water bulges outward because it's farther from the Moon and feels less pull than Earth's center does. As Earth rotates through these bulges, any given location experiences 2 high tides and 2 low tides each day. The Sun contributes about 40% as much tidal force as the Moon, despite being far more massive because it's also far more distant. Tides are gravity made visible, the Moon's grip on Earth's waters. Spring tides occur when the Sun, Moon and Earth align during new and full moons, combining their gravitational pulls. The gravitational tugs reinforce each other, creating higher high tides and lower low tides than usual. The name spring doesn't refer to the season but to the water springing forth with greater range. These enhanced tides happen twice monthly, marking the times when lunar and solar gravity work together rather than at cross purposes. Coastal communities have organized their lives around these celestial alignments for thousands of years. The gravitational dance of 3 bodies creates a rhythm in Earth's waters, a pulse timed by orbital mechanics. Neap tides occur when the Sun and Moon are at right angles to Earth during quarter moons, partially cancelling each other's effects. The Sun's gravity pulls perpendicular to the Moon's, creating smaller tidal ranges with lower high tides and higher low tides. The word neap comes from Old English meaning barely touching, describing how the tides seem diminished. These muted tides also happen twice monthly, alternating with spring tides in an endless cycle. The gravitational interplay creates a predictable rhythm in the oceans, a conversation between Earth, Moon and Sun written in the rising and falling of waters along every coastline throughout geological time. Earth's gravity shaped our planet into a sphere over billions of years, pulling matter equally in all directions toward the center. When Earth was young and molten, gravity smoothed out irregularities, pulling high points down and filling low points in. Any significant deviation from spherical shape creates uneven gravitational forces that flow and deform the planet until balance is restored. Only rotation prevents perfect sphericity, creating the slight equatorial bulge. Mountains can exist only because Earth's rocky crust is strong enough to temporarily resist gravity's smoothing influence. Given enough time and heat, gravity would erase every mountain and level every valley, rendering Earth perfectly spherical. Spheres are gravity's preferred geometry. The center of Earth is about 6,371 kilometers from the surface, a journey through increasingly dense and hot layers of matter. Gravity pulled the heaviest elements, iron and nickel, toward Earth's core during the planet's molten youth. The pressure at the core is about 3.6 million times atmospheric pressure, and temperatures reach around 5,400 degrees Celsius, as hot as the Sun's surface. Everything above pushes down on everything below, compressed by the weight of thousands of kilometers of rock. The core is gravity's creation, assembled by billions of years of matter falling inward. Earth's center is unreachable, unknowable except through seismic waves, yet it dominates the gravitational field we experience. Earth's gravitational pull on the Moon is what keeps it in orbit, a perpetual conversation between 2 worlds. The Moon falls toward Earth constantly, but its sideways velocity means it keeps missing our planet, tracing an elliptical path through space. If Earth's gravity suddenly vanished, the Moon would fly off in a straight line following Newton's first law of motion. But gravity bends its path into a closed loop, a cosmic demonstration of how force changes motion. Every 27.3 days the Moon completes this gravitational dance held by invisible strings of curved spacetime. The Moon is forever falling toward us, forever missing, caught in eternal orbit. The Sun contains 99.86% of the solar system's mass and dominates its gravity, holding 8 planets and countless smaller bodies in its grip. All the planets, moons, asteroids, comets and dust combined make up barely 0.1% of the solar system's mass. The Sun's overwhelming mass creates a gravitational field that extends for trillions of kilometers, defining the boundary of what we consider our solar neighborhood. Every object in the solar system ultimately orbits the Sun, held in place by its enormous gravitational influence. Even massive Jupiter is insignificant compared to our star. The Sun is the gravitational anchor of our cosmic home, the center around which everything else dances. Jupiter's gravity is so strong it affects the orbits of all other planets, creating subtle perturbations that ripple through the solar system. Jupiter is 318 times more massive than Earth, and its gravitational field shapes the asteroid belt, creates gaps in Saturn's rings and even causes the Sun itself to wobble. This wobble is how astronomers detect planets around other stars. They look for the gravitational tug of planets on their suns. Jupiter acts as the solar system's gravitational shepherd, its influence protecting Earth from some comets while redirecting others. In a very real sense, the solar system's architecture is partially Jupiter's creation, organized by its immense gravitational presence. If you could stand on Jupiter, you'd weigh 2.5 times more than on Earth, despite Jupiter being much larger. Jupiter's mass is enormous, but its radius is also large, placing its surface relatively far from its center where most mass concentrates. The combination produces surface gravity about 2.5 times Earth's. A person weighing 150 pounds on Earth would weigh 375 pounds on Jupiter. Your legs would struggle to support this weight. Your heart would work harder to pump blood upward against the increased pull. Walking would be exhausting, jumping nearly impossible. Jupiter's gravity creates an environment where human bodies, evolved for Earth's gentler pull, would be crushed by their own weight. Mars has only 38% of Earth's gravity, creating an environment where humans would feel surprisingly light. A 200-pound person would weigh just 76 pounds on the Martian surface. You could jump nearly 3 times higher than on Earth, carry heavier loads with ease, and feel a spring in every step. But this weak gravity creates problems for long-term habitation. Bones would lose density, muscles would atrophy, and the cardiovascular system would weaken without Earth's resistance to work against. Mars couldn't hold a thick atmosphere against solar wind with such weak gravity. The planet that once might have harbored oceans lost them partially because gravity's grip wasn't strong enough to hold them. Venus has about 91% of Earth's surface gravity despite being nearly the same size and density as our planet. With a radius about 95% of Earth's and a mass about 82% of Earth's, Venus produces a gravitational pull that feels almost like home. The similarity in gravity is one reason Venus is sometimes called Earth's sister planet. You'd barely notice the difference if you could stand on its surface, though the crushing atmospheric pressure and heat would kill you instantly. This gravitational similarity makes Venus an intriguing candidate for eventual human exploration, at least in terms of helping bodies adjust. Among rocky planets, Venus is Earth's gravitational twin, pulled from the same template. Mercury, the smallest planet, has only 38% of Earth's gravity, the same as Mars, despite being a different size. Mercury is smaller than Mars but much denser, packed with heavy metals, especially iron. The high density compensates for small size, producing comparable surface gravity to the larger but less dense Mars. This weak gravity has allowed solar wind to strip away most of Mercury's thin atmosphere over billions of years. The planet retains only a tenuous exosphere, constantly being replenished and lost. Mercury's gravity tells a story of a world that couldn't hold onto an atmosphere, exposing it to temperature swings of 430 degrees Celsius between day and night. Weak gravity left it vulnerable. Saturn's moon Titan is larger than our moon and has weaker surface gravity due to its lower density. Titan is the second largest moon in the solar system, bigger than the planet Mercury, yet its surface gravity is only 1.35 meters per second squared compared to our moon's 1.62. The difference comes from composition. Titan is made largely of water ice and lighter materials, while our moon is rocky and denser. On Titan, you could jump higher and fall more slowly than on our moon. Combined with Titan's thick atmosphere, the weak gravity makes it theoretically possible for humans to fly with wings attached to their arms. Titan's gravity creates a landscape of gentle forces. The asteroid belt exists where Jupiter's gravity prevented a planet from forming, disrupting coalescence of the rocky material that gathered there. About 2.2 to 3.2 astronomical units from the Sun, millions of rocky fragments orbit in the region between Mars and Jupiter. In the solar system's youth, these rocks might have accumulated into another terrestrial planet, but Jupiter's enormous gravitational influence stirred them into chaotic orbits. Collisions became destructive rather than constructive, shattering larger bodies instead of building them. Jupiter's gravity created gaps in the belt where its orbital resonances flung asteroids elsewhere. The asteroid belt is a planet that never was, prevented by gravity's disruptive influence from across space. Gravity keeps Saturn's rings in place while also slowly pulling them inward toward the planet. The rings are made of countless ice particles, from dust-sized grains to house-sized chunks, each orbiting independently. Gravity holds them around Saturn while preventing them from collapsing into a moon. But the rings are slowly raining down onto Saturn. Particles lose energy through collisions and electromagnetic interactions, gradually spiraling inward. Scientists estimate the rings may disappear completely in 100 million years, making them a temporary feature in cosmic terms. Saturn's rings are frozen in a transitional state between scattered debris and total consumption, caught momentarily in gravity's slow-motion embrace. Neptune was discovered mathematically by calculating gravitational effects on Uranus before anyone saw it through a telescope. Uranus's orbit didn't match predictions based on the known planet's gravitational influences. Astronomers hypothesized an unknown planet was tugging on Uranus, perturbing its path. By analyzing these perturbations, mathematicians calculated where this unknown planet should be. When astronomers pointed their telescopes at that location in 1846, there was Neptune, almost exactly where mathematics had predicted. It was one of the great triumphs of gravitational theory, predicting the position of an unseen world using nothing but equations and observation of another planet's subtle wobbles. Gravity betrayed Neptune's location. Pluto and its moon Charon orbit a point in space between them called the Bowery Center because their mutual gravity creates a shared center of mass. Charon is exceptionally large compared to Pluto, about 1/8 its mass and half its diameter. Instead of Charon simply orbiting Pluto, both worlds orbit a point in empty space between them. They're gravitationally locked in a mutual embrace, each always showing the same face to the other, spinning in synchrony. Technically, they constitute a binary dwarf planet system rather than a planet and moon. Their orbital dance demonstrates that gravity creates partnerships, not just hierarchies, when masses are comparable. Comets follow elliptical orbits determined entirely by the Sun's gravity, some taking thousands of years to complete a single orbit. Their paths are extremely elongated ellipses, spending most of their time in the distant, frozen outer solar system before making brief passes near the Sun. As they approach, the Sun's heat vaporizes their ice, creating the characteristic glowing coma and tail. Gravity determines when and where each comet appears in our sky. Some comets have such elongated orbits that they spend 99.9% of their lives in darkness and cold, warmed and illuminated for only a few months per orbit. They are prisoners of the Sun's gravity, condemned to endless elliptical journeys. The Oort cloud exists at the edge of the Sun's gravitational influence, a spherical shell of trillions of icy objects extending nearly a light year from the Sun. This is where the Sun's gravity is barely stronger than the gravitational tug of passing stars. The Oort cloud defines the true boundary of our solar system, the farthest realm where the Sun's gravity still dominates. Objects there move so slowly in their orbits that a single journey around the Sun takes millions of years. Occasionally, a passing star's gravity nudges an Oort cloud object inward, sending it on a long fall toward the Sun where we see it as a new comet. The Oort cloud is gravity's twilight zone. Gravity slingshots allow spacecraft to gain speed by using planets' gravitational fields as a boost, stealing a tiny bit of the planet's orbital energy. As a spacecraft approaches a planet, the planet's gravity accelerates it. If the trajectory is carefully planned, the spacecraft can whip around the planet and depart faster than it arrived, gaining momentum from the planet's own motion. This technique has enabled missions to the outer solar system that would otherwise be impossible with current rocket technology. The Voyager probes used gravity assists from Jupiter, Saturn, Uranus, and Neptune. We've learned to surf gravity's curves, turning planets into cosmic accelerators. The Voyager probes used gravity assists from multiple planets to reach the outer solar system, threading a cosmic needle that only aligned once every 176 years. Launched in 1977, Voyager 1 and 2 used Jupiter's gravity to accelerate towards Saturn, then Saturn's gravity to boost speed and redirect their paths. Voyager 2 continued to Uranus and Neptune, each encounter both speeding it up and bending its trajectory. Without these gravity assists, the missions would have required impossibly large amounts of fuel or taken decades longer. The alignment of planets was a gift from orbital mechanics. Gravity transformed distant worlds into stepping stones, carrying our furthest messengers toward interstellar space. Neutron stars have gravity so intense that a sugar cube-sized amount of their material would weigh 1 billion tons on Earth. These collapsed stellar cores pack 1 to 2 times the Sun's mass into a sphere only about 20 kilometers across. The density is incomprehensible, about 1 billion tons per teaspoon, approaching the density of atomic nuclei themselves. The matter is so compressed that electrons and protons merge into neutrons, creating a giant atomic nucleus held together against its own intense gravity only by neutron degeneracy pressure. A neutron star is matter's last stand against complete gravitational collapse, the densest stable form of matter we know can exist. A neutron star's gravity is about 2 billion times stronger than Earth's, creating an environment where physics reaches extremes. The escape velocity is about half the speed of light. The intense gravity creates mountains on neutron star surfaces that are at most a few millimeters tall because gravity's pull is strong enough to flatten anything higher. Light is bent so strongly that you could see around the star to its far side. Time flows dramatically slower on the surface compared to distant space. Falling onto a neutron star would accelerate you to relativistic speeds before the tidal forces ripped you apart at the atomic level. These are worlds where gravity has grown monstrous. Black holes have such extreme gravity that nothing, not even light, can escape once it crosses the event horizon. Here, gravity has overwhelmed every other force in nature, crushing matter into a mathematical point of infinite density called a singularity. The region around this singularity where escape becomes impossible is the event horizon, a one-way boundary in space-time. Anything crossing this boundary is causally disconnected from the outside universe forever, unable to send information or light back out. Black holes are regions where space-time curves into itself so extremely that it creates a trap from which nothing returns. They are gravity's final victory, points where the universe folds in on itself. The event horizon is the point of no return around a black hole, the boundary beyond which escape requires faster than light travel. For a non-rotating black hole, the event horizon forms a perfect sphere around the singularity. Its radius depends only on the black hole's mass. More massive black holes have larger event horizons. This boundary isn't a physical surface but a location in space-time where the escape velocity equals light speed. From outside, you can watch objects fall toward the event horizon, appearing to slow down and freeze at the boundary due to extreme time dilation. But for the falling object, nothing special happens at the horizon. They pass through without sensing the boundary, doomed to fall toward the singularity. At the center of most galaxies, including the Milky Way, sits a supermassive black hole with gravity so intense it governs the motion of billions of stars. These black holes contain millions to billions of solar masses compressed into regions smaller than our solar system. They likely formed in the early universe and grew by consuming gas, dust, and stars over billions of years. The gravity of these central black holes shapes the structure of their host galaxies, influencing star formation and the motion of matter across thousands of light years. They are gravitational anchors, cosmic engines that help organize the visible structures of galaxies. Nearly every large galaxy harbors one of these dark hearts. The Milky Way's central black hole, Sagittarius A star, has a mass of 4 million suns compressed into a region about 17 times the sun's diameter. This sounds enormous, but it's actually a relatively small supermassive black hole. Some galaxies host monsters containing billions of solar masses. Sagittarius A sits about 26,000 light-years from Earth, and astronomers have watched stars orbit around it at speeds up to 5,000 kilometers per second. These stellar orbits reveal the invisible mass pulling them in curved paths. In 2022, astronomers captured the first image of Sagittarius A's event horizon, showing the shadow cast by its extreme gravity against the glowing material swirling around it. We have photographed our galaxy's gravitational center. Time stops at the event horizon of a black hole from an outside observer's perspective due to infinite gravitational time dilation. If you watched someone fall toward a black hole, you'd see them slow down asymptotically, appearing to freeze at the event horizon, their image becoming increasingly redshifted until they fade from view. Yet from the falling person's perspective, they'd cross the horizon in finite time, experiencing nothing unusual at that moment. This discrepancy isn't an illusion. Both perspectives are equally valid descriptions of reality from different reference frames. Time at the event horizon has become infinitely dilated relative to distant observers. The horizon is a place where spacetime's structure creates a permanent now for outside viewers. Spaghettification is the stretching effect of extreme tidal gravity near black holes, pulling objects into long, thin shapes like strands of pasta. The gravitational pull on the near side of an object exceeds the pull on the far side by enormous amounts when gravity is intense and distance is short. For a person falling feet first into a stellar mass black hole, the difference in gravitational pull between feet and head would stretch and tear the body apart long before reaching the event horizon. For supermassive black holes with larger event horizons, the tidal gradient is gentler and you might cross the horizon intact before tidal forces destroy you. Either way, the differential gravity ultimately shreds everything into elementary particles. White dwarfs have gravity about 350,000 times stronger than Earth's, creating a dense environment where a teaspoon of matter weighs as much as an automobile. These are the leftover cores of sun-like stars that have exhausted their nuclear fuel. Gravity has compressed them until electron degeneracy pressure, a quantum mechanical effect, prevents further collapse. They're typically about Earth-sized but contain roughly the Sun's mass. Their intense gravity creates such high surface temperatures that they glow white-hot for billions of years before slowly cooling. White dwarfs represent a stable endpoint of stellar evolution for most stars, held in equilibrium between gravity's crush and quantum pressure pushing outward. The escape velocity from a neutron star is about half the speed of light, requiring impossible energies to leave its surface. For comparison, Earth's escape velocity is only 11.2 kilometers per second, while a neutron star's is about 150,000 kilometers per second, roughly 45% light speed. Any rocket trying to launch from a neutron star would need to accelerate to relativistic speeds just to escape. Light itself is dramatically redshifted, climbing out of such a deep gravitational well. The intense escape velocity means neutron stars can barely hold onto atmospheres. Only the densest, heaviest elements remain bound. These are worlds where leaving requires approaching cosmic speed limits. Gravitational time dilation near a black hole means time passes much more slowly for someone near the event horizon than for distant observers. Minutes for someone hovering just outside a black hole could equal years for observers far away. This isn't science fiction, it's a measured prediction of general relativity. The closer to the event horizon, the more extreme the effect. This has practical implications. A space traveler could journey close to a black hole, spend what feels like a few hours, and return to find decades or centuries have passed. Black holes are potential time machines to the future, offering passage through time by trading proximity to extreme gravity for temporal displacement. The movie Interstellar accurately depicted time dilation near a black hole, showing 1 hour on a planet near the event horizon equaling 7 years on Earth. The film consulted physicist Kip Thorne to ensure gravitational effects were realistically portrayed. The planet Miller's World orbited extremely close to the massive black hole Gargantua, experiencing intense time dilation while somehow avoiding tidal destruction. While the exact scenario requires special conditions, the underlying physics is sound. General relativity truly predicts such extreme time differences in strong gravitational fields. The movie translated abstract equations into visceral drama, showing audiences how gravity warps not just space, but time itself, creating temporal chasms between different reference frames. Gravity waves from colliding black holes compress and stretch space itself, creating detectable ripples in the fabric of space-time. When two black holes spiral together, they accelerate to significant fractions of light speed before merging. In the final moments, they shake space-time violently, sending gravitational waves radiating outward at light speed. These waves alternately compress and stretch space as they pass, a phenomenon measured by LIGO detectors as changes in distance smaller than a proton's width. The waves carry away enormous amounts of energy, converting the mass-energy equivalent of several suns into pure space-time vibration. The universe rings from these collisions, audible to those with ears sensitive enough to listen. Some black holes spin at nearly the speed of light, dragging space-time with them in a phenomenon called frame dragging. As a black hole rotates, it pulls space-time along like honey stirred by a spoon. Near a maximally spinning black hole, nothing can remain stationary. Even light must orbit in the same direction as the black hole's spin. This dragged space-time creates an ergosphere, a region where enormous amounts of energy could theoretically be extracted from the black hole's rotation. The spin can be measured by observing how matter spirals into the black hole and how gravitational waves carry angular momentum away. Rotating black holes twist space-time into spirals, creating cosmic whirlpools in the fabric of reality. The most massive black hole discovered, Phoenix, a star, contains roughly 100 billion times the mass of our Sun. This monster sits at the center of the Phoenix cluster, about 5.8 billion light-years from Earth. Its event horizon would extend for hundreds of billions of kilometers, larger than our entire solar system. How such enormous black holes formed remains mysterious. They're too massive to have grown by accretion alone since the universe began. They may have formed from direct collapse of massive gas clouds in the early universe, or from mergers of many smaller black holes. These ultramassive black holes demonstrate that gravity can accumulate mass in quantities almost incompatible with human intuition, creating singular objects that outweigh entire galaxy clusters. Gravity caused the first stars to form from clouds of hydrogen and helium after the Big Bang, lighting up the universe. In the early universe, small density variations in the primordial gas created regions where gravity was slightly stronger. These regions pulled in more matter, becoming denser, which strengthened gravity further in a runaway process. Over millions of years, clouds collapsed under their own weight, compressing and heating until nuclear fusion ignited in their cores. The first stars probably formed a few hundred million years after the Big Bang, ending the cosmic dark ages. Without gravity to gather diffuse gas into dense balls, the universe would remain an expanding cloud of atoms, dark and featureless forever. Gravity powers stars by compressing their cores to temperatures and pressures high enough for nuclear fusion. The weight of a star's outer layers crushes inward, squeezing the core until hydrogen atoms are forced close enough to overcome electromagnetic repulsion and fuse into helium. This fusion releases energy that generates pressure pushing outward, balancing gravity's inward crush. A star is a sustained battle between gravity trying to collapse it and fusion pressure trying to expand it. For billions of years, this balance holds. When fusion fuel depletes, gravity wins. The star collapses, potentially rebounding in a supernova or compressing into a white dwarf, neutron star, or black hole. Gravity is both star maker and star destroyer. The universe's expansion is actually accelerating, working against gravity's attempt to pull everything back together. For the first few billion years after the Big Bang, gravity slowed the expansion as expected, but about 6 billion years ago, the expansion began accelerating. This discovery won the Nobel Prize in 2011 and shocked cosmologists. Something with negative pressure, dubbed dark energy, appears to dominate the universe's dynamics, overpowering gravity on the largest scales. While gravity tries to pull galaxies together, dark energy pushes them apart with increasing vigor. The universe will expand forever, accelerating endlessly with gravity unable to halt the flight. The final fate is determined by this cosmic tug-of-war. Dark matter is matter we can't see but detect through its gravitational effects on visible matter and light. Galaxies rotate faster than they should based on their visible mass. The outer stars should fly off into space unless additional invisible mass provides extra gravity. Gravitational lensing bends light around galaxy clusters more than visible matter can account for. Computer simulations show galaxies can't form properly without dark matter's gravitational scaffolding. We don't know what dark matter is made of. It doesn't interact with light and passes through normal matter like a ghost, yet its gravity shapes the universe's structure. We live in a cosmos where most matter announces itself only through its gravitational whisper. Dark matter makes up about 85% of all matter in the universe, with ordinary matter composing the remaining 15%. Everything you see, stars, planets, gas clouds, galaxies, represents a tiny fraction of the universe's total matter content. Dark matter forms a vast cosmic web, invisible filaments connecting galaxy clusters across billions of light years. Normal matter collects in the gravitational wells created by this dark scaffold. We are the minority matter, the luminous exception in a universe dominated by something we can barely detect. Yet without dark matter's gravity organizing structure in the early universe, galaxies wouldn't have formed and we wouldn't exist. We owe our existence to invisible matter. Dark energy is causing the universe's expansion to accelerate against gravity and constitutes about 68% of the universe's total energy density. Unlike dark matter, which clumps and strengthens gravity, dark energy appears uniformly distributed through space with constant density. It creates a kind of anti-gravity effect, a negative pressure pushing space apart. As the universe expands, the amount of dark matter per volume decreases, but dark energy's density remains constant, so dark energy becomes increasingly dominant over time. Eventually, dark energy may tear apart galaxy clusters, then galaxies, then solar systems, then atoms themselves in a scenario called the Big Rip. The universe's ultimate fate hangs on the nature of dark energy. Galaxy clusters are held together by their combined gravitational pull, containing hundreds to thousands of galaxies spanning millions of light years. The space between galaxies in a cluster is filled with hot X-ray emitting gas, heated by the gravitational compression of falling into the cluster's gravitational well. These clusters are the largest gravitationally bound structures in the universe. Beyond this scale, dark energy's repulsion overpowers gravity's attraction. The Virgo cluster, containing over 2,000 galaxies, dominates our cosmic neighborhood. Galaxy clusters demonstrate gravity's organizing power. Given enough time and mass, gravity gathers diffuse material into hierarchical structures of increasing size. The Great Attractor is a gravitational anomaly pulling our galaxy and thousands of others toward it at about 600 kilometers per second. This massive concentration of matter lies about 150 to 250 million light-years away, hidden behind the Milky Way's disk, which obscures our view in that direction. The gravitational pull is enormous. It dominates the motion of our local supercluster. Observations suggest the Great Attractor itself is being pulled toward an even larger structure, the Shapley supercluster. We live in a universe of motion where gravity orchestrates flows of galaxies across cosmic distances like currents in an ocean. Even our galaxy is swept along in gravitational tides we're only beginning to map. Gravitational lensing allows us to see galaxies that would otherwise be hidden behind massive objects like galaxy clusters. The intense gravity of foreground clusters warps space-time so severely that light from background galaxies follows curved paths around the cluster. From Earth, we see multiple distorted images of the same background galaxy, sometimes stretched into arcs or even complete rings around the lensing cluster. This effect lets us observe galaxies that are farther and fainter than we could otherwise see. Gravitational lensing turns massive galaxy clusters into natural telescopes, magnifying the distant universe. Einstein's prediction of light bending becomes a tool for cosmic exploration. Einstein rings are circular distortions caused by gravitational lensing when a distant galaxy, a massive foreground object, and Earth align perfectly. The background galaxy's light spreads into a complete ring around the lensing object, creating a luminous circle in space. These rings are rare because they require nearly perfect alignment across cosmological distances. When discovered, they're named Einstein rings in honor of his prediction that gravity would bend light. They're visual proof of space-time curvature, photographs showing how mass warps the geometry of light's path. The universe occasionally arranges itself to demonstrate fundamental physics, creating symmetry from gravity's distortion of space-time. The cosmic web is the large-scale structure created by gravity over billions of years, organizing matter into filaments, walls, and voids. From a distance, the universe resembles a three-dimensional spiderweb, dense filaments of galaxies connected at intersections where massive galaxy clusters reside, surrounding enormous voids containing relatively little matter. This structure formed as gravity amplified tiny density fluctuations from the early universe, dense regions pulled in surrounding matter, becoming denser still, while underdense regions lost matter and became voids. The pattern reflects the initial conditions of the universe, grown and elaborated by billions of years of gravitational evolution. We live within this cosmic web structure. Superclusters are the largest gravitationally bound structures in the universe, containing dozens of galaxy clusters and spanning hundreds of millions of light years. These represent the maximum size at which gravity can overcome the universe's expansion and hold matter together. Beyond supercluster scales, dark energy's repulsive effect dominates and structures fly apart faster than they can merge. Superclusters sit at the nodes of the cosmic web, the largest peaks in the universe's density distribution. They mark the upper limit of gravity's organizing influence, the boundary where cosmic expansion wins the battle against gravitational attraction. They are islands of gravitational cohesion in an expanding sea. The Laniakea supercluster contains our Milky Way and 100,000 other galaxies spanning 520 million light-years across space. The name Laniakea comes from Hawaiian words meaning immeasurable heaven. This supercluster isn't held together by gravity. At this scale, cosmic expansion dominates, but represents the region of space where galaxies move together under shared gravitational influences. Laniakea was only mapped in 2014 using measurements of galaxy velocities that reveal gravity's invisible flows. We're part of this vast structure, residents of one small galaxy in a cosmic neighborhood containing 100,000 others. Understanding our place in Laniakea helps us comprehend our address in the universe. Gravity waves traveling through space were created by cataclysmic events billions of years ago, colliding black holes, merging neutron stars, and exploding supernovae. These waves have crossed enormous distances to reach Earth, carrying information about events that occurred in the distant past. Each detected gravitational wave opens a window to violence in the cosmos, moments when gravity reached such extremes that spacetime itself shook. Some waves come from events so energetic they converted several solar masses of matter into pure gravitational radiation in fractions of a second. We're detecting the aftershocks of cosmic catastrophes, feeling spacetime vibrate from impacts that occurred before Earth existed. The LIGO detectors can measure changes in space smaller than a proton's width, detecting gravitational waves by observing how they stretch and compress spacetime. Each detector consists of two 4-kilometer-long arms arranged in an L shape. Laser beams travel down each arm and back, and when a gravitational wave passes through, it slightly changes the arm's relative lengths. The precision required is astounding. LIGO can detect length changes of 10 to the minus 19th meters, less than 1,000th the diameter of a proton. This sensitivity has opened a new window on the universe, letting us listen to gravitational waves rather than just look at electromagnetic waves. We've gained a new sense for experiencing the cosmos. Gravity causes your blood to pool in your legs when you stand up, which is why you can feel dizzy if you rise too quickly. Your cardiovascular system constantly battles gravity to pump blood upward to your brain against a pressure gradient. Stand up suddenly, and blood flow to the brain temporarily decreases until your blood vessels constrict and heart rate increases to compensate. This is orthostatic hypotension, a brief victory of gravity over circulation. Your body evolved elaborate mechanisms to counteract gravity's effect on blood distribution. Every moment you stand, your heart works harder because gravity pulls blood downward. The simple act of standing requires continuous active resistance to gravitational force. Astronauts lose bone density in space because gravity isn't compressing their skeletons, removing the mechanical stress that signals bones to maintain density. On Earth, your bones constantly rebuild themselves in response to gravitational loading. In microgravity, this stimulus disappears and bone resorption exceeds bone formation. Astronauts can lose 1 to 2% of bone mass per month in space, particularly in weight-bearing bones like hips and spine. They must exercise for hours daily using resistance machines to partially compensate. After returning to Earth, it can take years to fully recover lost bone mass. Gravity isn't just a force we overcome, it's a necessary stimulus that maintains our structural integrity. Plants use gravity to determine which direction to grow their roots downward and stems upward through a process called gravitropism. Specialized cells in plant tissues contain dense, starch-filled organelles called statoliths that settle to the bottom of cells in response to gravity. This settling triggers signaling cascades that redirect growth hormones, causing roots to curve downward and shoots to curve upward. Plants grown in space exhibit random growth directions until given artificial gravity or other directional cues. Even simple organisms evolved to use gravity as a compass, orienting themselves in three-dimensional space by detecting which way is down. Gravity provides universal orientation for life on Earth. The inner ear uses gravity to help you maintain balance through the vestibular system's otolith organs. Tiny calcium carbonate crystals called otoliths rest on hair cells in fluid-filled chambers. When you tilt your head or accelerate, gravity and inertia cause the otoliths to shift, bending hair cells and sending signals to your brain about your head's orientation and movement. This system works continuously, giving you an unconscious sense of which way is up and detecting linear acceleration. Inner ear infections or damage can disrupt this system, causing vertigo, a distressing loss of gravitational reference. Your brain relies on gravity's constant pull to construct a stable sense of your body's position in space. Hydroelectric dams harness gravity's pull on water to generate electricity, converting gravitational potential energy into electrical power. Water stored in reservoirs at high elevation possesses gravitational potential energy. When released, gravity accelerates the water downward through turbines, spinning generators that produce electricity. The greater the height difference and water flow, the more power generated. Hydroelectricity provides about 16% of global electricity, all powered by the same force that makes apples fall. We've learned to exploit gravity's relentless downward pull, using Earth's gravitational field as an energy storage system. Gravity becomes an ally, its constant attraction transformed into useful work. Roller coasters use gravity to create the sensation of weightlessness during freefall moments when riders accelerate downward at 9.8 meters per second squared. At the top of hills and during drops, riders experience reduced or zero normal force. The floor isn't pushing up on them as forcefully, creating the stomach-dropping sensation of near weightlessness. Inversions produce brief moments of negative g-forces as the track curves faster than freefall. Designers carefully choreograph these gravitational experiences, using gravity as both accelerator and brake. The thrill comes from experiencing unusual gravitational states, being lifted, dropped, and spun while gravity remains constant, but our reference frame changes dramatically. We've turned gravity into recreation. Gravity makes flames point upward by pulling cooler, denser air downward, which displaces hot combustion gases upward. Fire heats air, reducing its density. The denser, cooler surrounding air is pulled down by gravity more strongly, flowing underneath and pushing the lighter hot gases up, creating convection currents. This is why flames are teardrop-shaped on Earth. In microgravity, flames burn as small blue spheres because no convective flow occurs without gravity to separate hot and cool gases. Candles are impossible to burn on spacecraft except in moving airflow. Even combustion's appearance depends on gravity organizing hot and cool gases by density. Gravity gives fire its familiar shape and behavior. Pendulum clocks rely on gravity's consistent acceleration to keep time, swinging at a period determined by pendulum length and gravitational strength. Galileo discovered that pendulum period depends only on length and gravity, not on swing amplitude or bob mass. This made pendulums perfect for regulating clocks. Gravity provides the steady timing reference. For centuries, pendulum clocks were the most accurate timepieces available, accurate to seconds per day. They work only on Earth because they require consistent gravity. Take one to the moon and it would run slower due to weaker gravity. For hundreds of years, humanity's most precise timekeeping depended on gravity's reliable pull. Gravity drainage systems move sewage and water without pumps by allowing gravity to pull fluids downhill through sloped pipes. Ancient Romans built aqueducts using gravity to transport water across miles, carefully calculating slopes to maintain flow without excessive speed that would erode channels. Modern cities use gravity sewers where possible, requiring only occasional pumping stations to lift wastewater when necessary. This passive system is reliable and energy efficient. Gravity works continuously without electricity or maintenance. The principle is ancient and simple. Build downhill paths, and gravity will move fluids for free. Sometimes the oldest technologies remain the best because they harness fundamental forces requiring no external power. Aircraft fuel calculations account for air density and mass rather than the negligible change in gravity at altitude. While gravity decreases slightly at cruising altitude, the effect, about 0.3% weaker at 35,000 feet, is inconsequential for flight planning. What matters is air density, which decreases dramatically with altitude, reducing both lift and drag. Pilots and engineers calculate fuel needs based on aircraft mass, air density, wind, and distance, not gravitational variations. The confusion arises because we often think of weight changing with gravity, but aircraft performance depends on mass and aerodynamic forces. Gravity's small variation with altitude is overshadowed by enormous changes in atmospheric properties that profoundly affect flight physics. Scientists still don't fully understand how gravity works at quantum scales where particles exist in superpositions and exhibit wave-particle duality. General relativity describes gravity beautifully at large scales but doesn't incorporate quantum mechanics. Quantum field theory describes the other three forces successfully but can't accommodate gravity. When we try to quantize gravity using standard techniques, we get nonsensical, infinite results. This tension between quantum mechanics and general relativity is one of physics' central problems. We don't know what happens to spacetime at the Planck scale, approximately 10 to the negative 35th meters, where both quantum and gravitational effects become equally important. Gravity remains partially mysterious at the smallest scales. String theory attempts to unify gravity with quantum mechanics by proposing that fundamental particles are actually tiny vibrating strings. Different vibration patterns correspond to different particles. One pattern creates electrons, another creates photons, and a specific vibration creates gravitons, the hypothetical quantum particles of gravity. String theory requires additional spatial dimensions beyond our familiar 3, usually 6 or 7 extra dimensions curled up so small we can't detect them. If string theory is correct, gravity would finally fit into the quantum framework. But string theory remains unproven, making predictions difficult to test with current technology. It's elegant mathematics seeking physical confirmation, a possible answer to gravity's quantum puzzle. Quantum gravity remains one of physics' greatest unsolved mysteries, the missing piece needed to fully understand how the universe works. We need quantum gravity to describe black hole singularities where both quantum effects and gravity are strong. We need it to understand the first moments after the Big Bang when the entire universe was quantum-sized. The theory might reveal whether black hole singularities are real infinities or finite quantum structures. It could explain dark energy or even dark matter. Whatever form quantum gravity takes, whether string theory, loop quantum gravity, or something yet undiscovered, it will revolutionize our understanding as profoundly as Einstein's relativity did. The answer awaits discovery. Some theories suggest gravity might leak into other dimensions, which could explain why it seems so weak compared to other forces. If our four-dimensional space-time is embedded in a higher dimensional space, gravity might spread into these extra dimensions while other forces remain confined to our 4 dimensions. This leakage would dilute gravity's strength in our dimensions, explaining its weakness. At extremely short distances, smaller than the size of extra dimensions, gravity might become much stronger than we observe at larger scales. These theories are speculative but testable. Particle colliders might detect evidence of extra dimensions if they exist. Gravity's weakness might be evidence that our familiar dimensions are not the whole story. Anti-gravity remains purely theoretical. No known force can cancel or repel gravity in the way that positive and negative charges can cancel electrical effects. We can counteract gravity's effects with other forces. Electromagnetic forces levitate trains, centrifugal forces simulate weightlessness, but we cannot block or negate gravity itself. Unlike electromagnetism with its positive and negative charges that attract and repel, gravity only attracts. There's no negative mass to create repulsive gravity. Every attempt to create anti-gravity has failed or relied on other forces masquerading as gravity control. Gravity cannot be switched off, shielded against, or reversed. It remains the one force we cannot escape, only overcome temporarily with expenditure of energy. Gravity's attraction is absolute and universal. And so we've journeyed through 100 truths about gravity, the invisible thread connecting every atom in the cosmos. Right now, it holds you gently against the Earth, keeping you safe while planets orbit and galaxies spin in their ancient dance. Gravity shaped the universe and shaped you, a force so weak a butterfly defies it, yet so powerful it bends light and time. As you drift towards sleep, know that you are held, always held, in gravity's eternal embrace. Good night, friend. Rest well, and I'll see you on our next sleepy science journey.